Hi everyone. This series of videos is going to take us through the last major topic that's going to be included on the AP test called accumulation. Accumulation is really just a natural extension of what we were doing with the second fundamental theorem of calculus in the previous lessons. So hopefully this will tie together some of those ideas in a way that suggests that this whole chapter, and really chapter 4, is all just one cumulative reiteration of what it means to take an integral, which is to find an area and to analyze that area in the context of real life situations. This specific playlist of videos covering pages 11 through 13 is meant to introduce you to the concept of accumulation and what types of problems we would consider to be accumulation problems. The first bit of page 11 up at the top there is meant to give you some context about the word accumulation and to what it refers. So I would suggest, if you need a second to read it, that you pause this video and read the paragraph to give yourself a bit of context. I'll try to summarize very quickly what this paragraph is saying, but again, if you need some time to read it and analyze for yourself, I recommend that you do that now before we get too far into things. The accumulation that you'll be seeing throughout this throughout this section is really just referring to the idea that we're gradually building up a bigger and bigger region that we're integrating. So the integrals that we're going to be doing are going to show an accumulation by gradually including more and more space under the curve that we're going to analyze. In example number 1, you can get a preview of this by looking at the integral symbol in the table and recognizing that those x values are possible places where the area, or the integral, will end. So the first integral is from 0 to 0, the next integral is from 0 to 1, the next integral is from 0 to 2, the next integral is from 0 to 3, the next integral is from 0 to 4, and the last integral is from 0 to 5, which means I'm going to keep gradually accumulate more and more area, 0 to 0, 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5, and as I accumulate that area, I can definitely expect the area to get bigger, and I can definitely expect the value of the calculus to get bigger. So that's something that we're going to explore a little bit, and I definitely want to make sure that you have a sense of why we would do that, so that when we understand it in the context of a simple problem, we can extend it to more analytical terms in contextual situations, like in example 3, which is going to talk about snow accumulation, or later in the chapter, which gets into some kind of dicey stuff, but the rate at which we burn calories while exercising. So this idea of accumulation generally just refers to the idea that if you allow more time to keep stretching on, things are going to build up and build up and build up. Let's start to look at some accumulation in context so we can better understand why we need to analyze this buildup at all. In example number 1, it's asking you to consider that function, f of t equals 2. Okay, so 2, pretty basic function. It's asking us to sketch that function on these axes. So just as a reminder, 2 would be a horizontal line that touches the y-coordinate of 2. So I'll just quickly make that horizontal line there. So that's my function. Not much to have to look at, so I'm just going to kind of leave it there. It says in letter B to consider that expression, which is a familiar looking integral by now, called the accumulation function. We've never really been calling it an accumulation function, we've just thought of it as an integral, but accumulation is going to be synonymous with integral, just like we've had other synonymous word associations in the past. Accumulation, integral, antiderivative, area, those are all now synonymous with the same idea. So to complete this table with the integral in mind, I'm going to just go one step at a time and think about each of these possible situations as a separate problem. In other words, I'm going to think about each of these possible x values as a possible upper limit for the integral that they're giving me. So the first spot in the table would be the integral from 0 to x coordinate 0. In the context of the graph, the area from 0 to 0 seems like it's not going to be even possible to find, because if I'm starting at 0 and ending at 0, the base of my area is going to be 0. So even though I might have a height, 0 times whatever the height is just going to give me an area of 0. So notice I'm interpreting this as an area problem. I could do an antiderivative if I wanted to, but for now I'm just going to think of it as an area. I'll go back and think of it as an antiderivative later to see if that would change my mind, but I'm thinking that this is a relatively nice looking graph, so doing it as an area just seems intuitive because these are going to be nice little areas. Let's do the next one, the area from 0, which is fixed, to 1, my new x coordinate in the next row of the table. So for the area from 0 to 1, f of t dt is just a formality. That's just telling us what function we're analyzing. So the area from 0 to 1 now, from 0 to 1 would have a base of 1 and a height of 2, and it would look like a rectangle. That area under the curve is this rectangular region that I'm shading in. So if I find the area of that region, it looks like the area is 1 times 2, positive times positive, area would be 2. Now, of course, I'm going to keep doing this whole process. The next x coordinate is referring to the area from 0 to 2. So notice I'm taking the x coordinate and just plugging it in as the upper limit in my accumulation function. So the integral from 0 to 2 is just the area from 0 to 2. Now the integral from 0 to 2 I've already kind of partially done, so I'm just going to shade a little bit more space to represent the new section. And now I'm going to picture the region from 0 to 2. In total, that would be a base of 2, height of 2, so that gives me a total area of 4. Notice how in context we keep talking about the total area from 0 to 2. I'm not just finding the one new shaded rectangle, I'm finding the total area from 0 to 2. Hence, the area is accumulating more and more space the further I extend it out. Now, I'm going to leave the rest of the table up to you as a quick task for you to do so that you can start to see the accumulation for yourself. Start to notice what happens when you get your answers to 3, 4, and 5. What's accumulating? And does that make sense, that use of the word? In the next video, we'll finish question number 1, but take the time between now and the beginning of the next video to finish this table and to try, if you can, to answer questions C and D so that you can get some of those observations in your own words and make them a little bit more powerful.